So this is going to be a very short and brief tutorial, maximum of couple of lectures, I guess, on Verilog HDL. The intent is to just give you some idea about the language, and then you have to pick up that language on your own for all the assignments that will follow. So this is what we are going to take a look at, is that we are going to look at structural hardware models. How do you represent different structural gate level circuits in Verilog? I'll give you some idea about 4-valued logic which is followed in Verilog. How do we model delay? How do we instantiate different modules in a design? How is the wiring between the modules done? How do you write a test bench? Then what are behavioral models in Verilog or system Verilog? Concurrency handling between these models, and the summary. Now the source of what I will cover here is mainly from this book, the Verilog Hardware Description Language by Thomas and Moody, and published by Kluwer Academic Publishers. And these slides have been taken from the site of Professor Mike Bushnell. So I will quickly go through the Verilog language constructs. So what are structural models? These are built from gate primitives and or other modules. Okay, so it actually describes the circuit at the structural level, not in terms of the not in terms of a behavioral model. Okay, so we don't have things like if then else or for loop here. Right? We have gates, their interconnections, modules which contain gates, and then interconnection between modules and things of that nature. They describe the circuit using logic gates, much as you would see in an implementation of a circuit. So let us look at this example. In this example, this is an example of a multiplexer which has the output F, and we have the two inputs A and B between which it multiplexes, and ACL is the select line. So you can see in Verilog we are defining the module mux with these parameters. These are the inputs and outputs, and then we declare the outputs, we declare the inputs. Then we describe each gate. So let's say that when we take this gate, this one, then for this one we have, it's an AND gate. This is the transport delay of the gate, the delay that it takes for the input to propagate to the output. So 5 units of delay, G1, F1, A, N cell. So F1 is the output, A and N cell are the inputs. Okay, and the type of the gate is AND. G2 is also an AND gate, which is this one. So as you can see here, we have a comma. Okay, so just like you have in C, you can declare int A comma B comma C. So you are declaring G1, then G2, which is F2 B ACL. Okay, now that's because its output is F2 and B and ACL are its two inputs. Okay, then we have this OR gate, this one. This OR gate has output of F and inputs of F1 and F2, right? And then we have this NOT gate, this one, and this NOT gate has input is ACL and the output is NACL. Okay. Now these lines, this F1, F2 and N cell, they are wires, but they are not declared as wires here, because the outputs of gates by definition are wires. So we don't have to explicitly declare them. So you can see in this declaration there is no F1, there is no F2, there is no N cell. They are by default wires. All right. And similarly, all the primary inputs, the inputs that are fed into the circuit, they are also wires. Okay, by definition. So we can use them wherever we want. Right. There is a simple view of the multiplexer implemented in the gate level. So, in the gate level models, we need to model the gates, their functions and their delays. So, Verilog has the following types of gates. It has NAND, it has NOR, it has AND, OR, XOR, XNOR. You can have a buffer, and you can have the NOT gate, okay, and a few others, right? But you can define your own functions also. You can define modules which are compositions of different gates. The gates operate on input values producing an output value. The typical Verilog gate instantiation is of this type. You have the gate name or the type, which is one of these, and then you have the delay. Now this is optional. Okay, it's optional to specify that that this is a delay. Then you have the instance name, and then first is the output of the gate, and then the inputs of the gate. So you can have 2 input, 3 input, 4 input, have as many number of input gates. All right. And then if you want to specify more than one instance, then as we have seen previously, that instead of giving the semicolon, you give a colon and then add the other gate names, and then finally put the semicolon. Okay, just like variable declarations. Is that clear? Now, in Verilog we have 4 valued logic. What are the logic values? They are 1, 0, X, which stands for unknown, and Z, which stands for high impedance. X is one of 1, 0, Z, or it could be even in the state of change. Okay, but which one of these we don't know. So it is not that it doesn't have a value. It has a value, but which value we don't know. That's why we call it unknown. Z is a high impedance output. Typically, if the output of a gate becomes tri-state, then that is Z. And it's very important because whenever you have a bus, for example, in a bus at a given point of time, somebody is driving the signals, one or more of the devices are reading the signals. Two gates should not drive, different devices should not drive the bus at the same time, because then we will have collision in the signals, right? So what is the other outputs that feed into the bus going to be in? So they are going to be tri-stated, right? So all except the current driver will be tri-stated, right? So that's why tri-state is a very important component, and we cannot simply ignore tri-state. So what basis do they have in reality? 0, 1, 1, no question, it is our Boolean values. Z, a tri-state gate drives either a 0 or 1 on its output, and if it is not doing that, its output is high impedance. Okay? So if the output of a tri-state gate is not 0 or 1, then it is in high impedance. Tri-state gates are real devices, and Z is a real electrical effect. Right? So it is really that it has that value. X is not a real value, it is unknown. So the real value is something, but we don't know what value that is. Okay, it is typically used as a debugging aid. In many cases, you might want to treat something as a don't care, right? So at the beginning of the simulation, all values in the simulation will start as X. They are all unknown, and then you start defining them. Right? Verilog keeps track of more values than these in some situations, but we are not going to get into that right now. Logic with multi-level logic values. Logic with these 4 values makes sense. NAND anything with a 0 and you get a 1. Right? And anything with a 0 and you get a 0. This includes having X and Z as the other input. So if the other input is X or if it is Z, it doesn't matter. If in an AND or a NAND any input is 0, then the output is determined by that only. In case of AND, the output will be 0, in case of NAND, the output will be 1. and two x's and you get an x. Make sense? If you don't know the values of both inputs of a NAND gate, can you know the output of the NAND? No. So the output will also be x. Note that Z treated as an x on input. Their rows and columns are the same. Okay, now let us look at this one. If you forget to connect an input, it will be seen as a Z. If there is a input which is left hanging, then it will be treated as Z. At the start of simulation, everything is an X. Okay, and then slowly its value will get defined. So we are going to go into transport delay now. Okay, so let me. You want to do it? So let me talk about transport delay. So in transport delay, if I have a #5 transport delay, that would mean that it takes 5 units of time for the input to propagate to the output. So that's the delay that it takes here. Now, what would that mean in terms of simulation? It means that if your inputs are not steady for this amount of time, then the input may not be noted at all. Now, what kind of thing can happen there? Say for example, this is 1, this is held at 1, and what I feed here is a very narrow pulse. Alright. So this has a width less than #5, let's say. Then that means that this is not going to be present at the see momentarily the output should have been 1, but because of this delay you will not see that it is 1. Okay, because it doesn't it is basically, you can think of this as what is known as inertial delay. Inertial delay means you think that the gate has a inertia in responding to the inputs, and if you change the inputs within that period, then you will not see the output that you expect within that time. So this is that thing. This can even happen because of these two inputs being driven by two different clocks. So it could be the case that this one became 1 at some point of time and the other one was 1 and became 0 at this point of time. Alright, so these are the two inputs into your gate. Now, as you can see here that the point of time for which both were 1 is a very narrow point of time. Okay, and therefore we are not able to see that in the output. So in this model, no. Okay, so let us come back to the slides. What if the input changes during this time? So this is a NAND gate, let's say, which has 35 units of delay. F1 is the output, ABC are the inputs, 35 is the transport delay. What if the input changes during that time? How wide must an input spike be to affect the output? Okay, think of the gate as having inertia. The input change must be present long enough to get the output to change. That long enough time is called the inertial delay, and in Verilog this time is equal to the transport delay, the transport delay that you specify here. Okay. So right, so now
this is basically the higher delay. What is the reason for this?
this delay is the delay that the gate itself takes. See, what is how does a gate change its state? So the input that is fed here is is fed into some gate of some transistor, okay, in CMOS for example. Now there is a capacitance between that gate and the ground. So when this B rises for example, then that capacitance gets charged. So there is a charging delay for that, okay. So that is the delay of the gate, right. Similarly for discharging, when it goes from high to low, again the capacitor at the next at the nets which C is driving, they will discharge through this gate to ground, okay. So that discharging time is also the time for it to fall. So these are the actual delays that are there. Now in high level models like the ones that we are considering here, we use some ballpark figures to model those delays, okay. And in this case we are talking about fixed delays. These delays they are not different for different inputs, but there are also delay models where the delay from one input to C is going to be different from another input to C, okay. Now let's see how we compose two different blocks and create one larger block. So let us build a 2-bit mux, 2-bit multiplexer. So what we first do, now the picture that I am going to show is the way that we think about when we actually do the coding. So we first take two multiplexer blocks. These blocks are the ones for which we have already written the code, right. So we instantiate two of them in our wider multiplexer. This is our wider multiplexer in which we instantiate these two. Then we have to connect them by wires. Okay. How are we going to connect them by wires? So we will have one multiplexer multiplexing between A0 and B0, another multiplexing between A1 and B1, and we will use the same select line to select both multiplexers. So this is one thing, this is the other connection, and then this is the select connection, right. So this is the way in which we are going to develop the code also. So you can see here that we had defined this mux previously as a module couple of slides back. We are instantiating two copies of that here. So you can see that this is bit 1, which is a multiplexer having F1 as an output, A1, B1 and select as the inputs, and bit 0 is the other one. Note the comma here, which is used because we are declaring two of the same type, so we just separate them by a comma. You could have written them in two separate lines also. You could have put a semicolon here and then written mux bit 0 again. And now you see how is the wiring done. The wiring input, as I mentioned previously, all inputs are by default wires. So this input is actually wiring these two because we have used the same name here, right. And then this A1 and B1 are going from here to here, A0 and B0 are going from here to here, and F1, this, because it's the output of the mux, it's also a wire that is actually feeding into the output. F0 is also feeding out to the other output, right. So we did not have to explicitly define any wire here, okay. Modules and gate primitives are instantiated, which means that they are copied. Now it's not like a function call. In a function call, it is the same code which is executed. Here they are two separate physical entities. The mux1 and the mux2 are not the same thing. They are two physical hardware pieces. Right? So these are instantiated or copied. They are not called. Okay, please understand the difference between them. The two copies share the module definition. The same definition of mux is shared by the two. So if you change the original mux definition, If you change the functionality of the original mux, then the functionality of all these copies will change, right? However, the internal entities like the gate names, internal port names and other things to come are all private, separate copies. So in other words, if you think of this whole wide mux, then there are two mux modules in wide mux, and if you now if you are asked to count the number of gates, then it is actually 4 gates. So that's the sum of the number of gates in mux 1 and mux 2. There are 2 OR gates, okay, one from mux 1, one from mux 2, and there are 2 NOT gates, again one from mux 1, one from mux 2. Okay. Why is this cool? This is cool because you can define modules in whatever way you like and then reuse them, right? So other modules are built by instantiating the primitive gates, and then you can build other modules by instantiating other modules, right? So you can hierarchically build up your design. The design hierarchy of modules is built using instantiation. Now when we will refer to the module hierarchy, this is the hierarchy that we will refer to, okay? That modules, the modules that is instantiated within them, the modules that are instantiated within those submodules and so on. This is the design hierarchy, the module hierarchy. So you can use modules that you have already built and tested. You can hide the details because you are just instantiating the module. You see the inner part of that module is not visible in the top module. For example, when we had this one, see that the actual details of mux is not there here, which is good because you know it's a mux, right? You know what it is supposed to do. So its inner implementation, if you had actually flattened it out, then that would have cluttered up the code. So that's a good thing. It's the same advantage of using procedures in programming languages. So no one designs 1 million plus random gates. They are always use hierarchy, and we have actually talked something about the software analogies. So please think about that. Now, how does the data flow through these? So think of this module called put together, which has one copy of the module BBB and one copy of the module AAA. Okay, and just see how they are connected. So there are wires W1, W2, W3, W4. Okay, and they are used to connect them in this way. Okay, now what happens when out is set to 1? Now who is setting out to 1? There is only one driver for every signal. You cannot have more than one driver for a signal, unless of course there are tri-state buffers in between, right? So the one which is driving the signal is out 1, this one, this NAND gate. Now when the output of this NAND gate changes, then that being an output of the module AAA, this output will change. Now this output is instantiated as W2 in this top module, right? So this out1 is actually W2 here. So W2 will change here because the output of this Ricky has changed, and now that is wired to the input W2 of this. So this, when this changes, this W2 will change and also this W2 will change, because this one is driving both of them. Okay, so this BBB is the input here. So this W2 is then show as an input change in module BBB. Okay, and then that is going to change the input of this XOR gate and may actually change O1 also. Now do you see how the thing flows through from the output of one to the input of another, and then finally into the input of another, and that's the way it can propagate through. and the binding between these is done through wires. So it's W2 here, W2 here, they are linked by this wire. Is that clear? Right. So you have to get a flavor of the flow of the signal through the module hierarchy. Now implicit wires, so I already talked about this. So how come there are no wires declared in some of these modules? This module, for example, this module mux, it doesn't have a wire, right? Because gate instantiations implicitly declare wires for their outputs. So for example, F1, F2, N cell, these are wires are implicitly declared. All other connections must be explicitly declared as wires. For instance, connection between module ports like this W2, W2, these are wired together, and that is through this wire, right? And output and input declarations are wires. So you can use output and inputs which are defined here like F, A, B, select also as wires. How to build and test a module? So now we come to the test bench part of it. So we have some idea about how to write the design. Now we construct what is called a test bench for the design. So you develop your hierarchical system within a module that has input and output ports, which is called the design here. So the design is the actual circuit, the one that you actually want to finally tape out. Okay? And we develop a separate module to generate tests for the module. So let us call that the test module. Okay? The test module is again going to be written in Verilog. And we connect the test module with the design module with another module which is called the test bench. So it's the wrapper. And that is the top module, the test bench. And that is the one where simulation starts. So that's like your main. Okay. So within that main you have two components. One is the design under test, the other is the test module. Alright. And in system Verilog kind of languages you will also have the interface for binding the two. Right. And so that you can have the assertions sitting on top of that. So let us look at this example. So I have this module test which will typically have an initial block. That initial block is going to be the first thing that will be simulated. Okay, initial block by definition in Verilog is simulated before any of the other code is simulated. So in that block you will instantiate the initial values of all your signals, right? And then this is the design, and this is the test bench which is going to take the design and the test, and as you can see that it is going to link up these things. So L, L, M, M, all right. Okay. So and then this can also have its own initial block to set up the monitor and the display. So this reiterates what I have said just now. So this is the design, which is the DUT, design under test. This is the test module, and this is the test bench. Let us look at this example which has a half adder here, which is the design under test. The half adder has the sum as the output, and, the sum and the carry as the output, and A and B are the inputs. Okay, and it uses the XOR gate for computing the sum and the AND gate for computing the output. So all of you are familiar with half adder, right? Now, and the test bench is the bench which instantiates this half adder, and it also adds the test module, which is this test add. Okay, let us go into test add and see what it does. So it has the input as the sum and the carry out, because these are the outputs of the DUT. The DUT outputs are the inputs to the test, because it wants to see whether the values that it produces are correct or not. And the inputs, the outputs of this test add, namely A and B, are the inputs that are going to go into the half adder. Okay, they are the inputs to the half adder. So we declare them also as registers because they will have state. Okay, they will have to hold steady state values. So we declare them as registers. Then there is this initial block. What does this initial block do? It first of all sets up a monitor to print the values of A, B, sum and carry out. Then it sets A equal to 0, B equal to 0. Then what's that going to do? Whenever this assignment is made, the half adder will produce some output. That output will be displayed. Okay. Then after 10 units of time, you change B to 1. Okay. Then after 10 units of time, you change A to 1. So these are different test scenarios that you're doing. So you first tested with A equal to 0, B equal to 0. Then you are testing with A equal to 0, B equal to 1. Then you are testing with A equal to 1, B equal to 1. Why? Because see, these are registers. So when you after 10 units of time, the value of A is still held at 0 at this point of time. So A equal to 0, B equal to 1. And then after another 10 units of time, the value of B is still 1 here because it has been stored in the register. Right? So you are testing for all these 4 test scenarios and then you are going to $finish. Alright. Why do we have this 10 here?
It is allowing the output to change for such a
Right. So this is allowing the delay of the required for the last simulation step. When you are doing this with B equal to 0, A equal to 1, for that you need some time for the output to settle. Why? Because these gates have some inertial delay. So you have to wait until these gates settle. Right? And so you have kept a time of #10, assuming that by that time it's going to settle down. Right? And then $finish means that's the end of simulation. Right? So this whole module is integrated with this and linked through these wires. So when simulation starts, it is going to run for 10, 20, 30, 40 units of time and then terminate. Is that clear? Right? So this is an elaboration of the test module. So the $monitor prints its string when executed. So this is the string and it's very similar to C, so you can figure out what it is going to do. It's going to print A equal to %B for boolean and then B equal to %B for boolean, %B is for boolean. After that the string is printed when one of the listed value changes. So it will print it the first time and then thereafter it is going to print it every time when any of the listed values change. So if any of these change, it will print it. Okay, and it will also show you at what time, it is going to show you the timeline also, and you can actually plot it out on a display, so that you get timing diagrams. It shows that when the signals are changing. Only one monitor can be active at any time, and it prints at the end of current simulation time. Okay, now there's an important thing here is when does the monitor sample those values. Okay, that is also going to be important. I mean, at the beginning of the cycle or the end of the cycle. See, there is a point where the inputs are not stabilizing, right? So will it actually check after it has stabilized, or will it check it before any of the inputs are perturbed, right? So these are very important decisions, and when we go into the semantics of this, we are going to study that, because that is going to totally determine how we verify them. Now function of this tester is, as I said, that at time 0 it print values and sets A equal to B equal to 0, then sets this in this sequence. Okay, we have discussed this already.
Sir, in the test bed, are the inputs and outputs reversed?
are the inputs and outputs.
Reverse.
You can see these are positional parameters, and you the way you declare them is your choice. I mean, are you saying that why did I not write the outputs first and then inputs here?
No, no.
Then
In the half adder, the sum and cout was declared as output.
for the half adder module, the sum and cout are outputs, but these outputs are wired in as inputs of the tested. Huh. Uh, See, this SU is SU, this CO is this CO. These are your inputs, sum and cout. Okay. So and these are the outputs. The first two are the outputs for the half adder. The last two are the inputs of the test ad. So it's the positional parameters. Okay, just like you have in C. So you link it up like that. Does it make sense?
It's that A and that A also same.
This A and this A, yes. Because you see this A and this A, this B and this B. See, they are wired, so they are the same. So effectively, this sum is the same, is wired to this sum, and this cout is wired to this cout, which is what we want. We want to read the sum and the carry, and we want to drive the inputs A and B, right, from the test module. So where were we? Here. Okay. Now you can also have multi-bit things, like you see this output here is multiple bits. Okay, so 1:0, so it's a 2-bit output. This is a 2-bit register. Okay, now it acts as a 2-bit number, so you can count 0001 1011 00 etc. Okay, any of these values it can take. Module T bench needs to connect it correctly. Okay, module half adder has 1-bit ports, so this has 1-bit ports, right? So you see, if you declare this as a 2-bit wire, then this has to be declared as T1 and T0. Is that clear? So see, the input of the half adder previously in our definition was 2 separate inputs A and B. Now what we are doing here is we are saying that let the input be a 2-bit wire. So that means that this wire is a wire having 2 bits. So the bit 0 is here and bit 1 is here, right? So that's how we have to instantiate. Rest of it is similar.
Can't we just pass it as just T and access them separately in the...
If you could have declared in your half adder, you could have declared T to be a 2-bit input, but then this code will have to change. So then this code will have to be rewritten. Okay, so that this is not declared as 2 inputs A and B, but as 1 input A with 0:1. Right? Then again, these would have been A0, A1, and things like that. All right. Now, because this was written in this way, if we want to use it in a top module which has a multi-bit wire definition, then this is the way we are going to pass them. Okay. Very similar to array handling in programming languages. So if you have declared them as 2 separate integers, and then you just pass A0 and A1. Okay. And rest of this is the similar, except that now you see we have made this more slightly different, because now test is a 2-bit word. Okay, so we can actually have something like this: for test equal to 0, test less than 3, test equal to test plus 1, right? Because now test being a word can be treated as an integer. Okay, so it can take the value 0, 1, 2, 3. But if you put this as something like 4, then you are in trouble, because then you are overshooting the value which can be stored in this registered test. It's a 2-bit register.
Back to 0, 0.
it's an error first of all, because if you have a 2-bit register, then it cannot take a value which is greater than 3. Right. So if you try to assign it some value which is greater than 3 by test equal to test plus 1, then that is something which is an error. Right. Now, in what way that error is going to get manifest, will manifest itself? It may manifest itself as a warning, and the semantics will have to be looked at, that whether that will actually wrap around to a modulo 4 arithmetic, or whether it will actually show it as an overflow, is something that for which we will have to look up the semantics of the language. Right. Is that all right? Now, I am no expert in Verilog, so if you ask me nitty-gritties about the semantics, then so but that's the idea. I mean, you are not supposed to write something which is more than 3 in a 2-bit register. Okay. So we will conclude this with this slide, where we now move into behavioral models. Right. So far we have only talked about structural models and writing a test bench and wrapping it around the duty. Now, the structural model, it specifies the primitive gates and wires. It specifies it specifies the structure of a logical netlist, and you basically know how to do this now. The behavioral model is like a procedure in a programming language, and you still specify a module in Verilog with inputs and outputs, but inside the module you may not have gates and things like that. You can write code to tell what you want to happen. Okay, not what gates to connect to make it happen. So when you are saying that you are writing out gates, you are almost synthesizing the circuit. You are almost giving it in the circuit form. Whereas in the behavioral model, you are going to specify it in the algorithm form, and you will expect the synthesizer to take that and actually generate a circuit which does what this behavioral model does. Right. Now, this synthesis from a behavioral level to the structural level has been worked out to a large extent in digital designs. In analog designs, it is in its infancy, and there are two groups of people who, one school which feels that for analog this is never going to happen, and the other group which feels that in analog also, because we do the same thing repeatedly with minor changes, there is a potential of translating behavioral models into structure automatically. Now, why do you use behavioral models? You can use behavioral models for test bench modules to test structural designs. That is one of the important uses of that. See, your duty might actually work, it might be one component of a processor. What do I do with the other components of the processor? First of all, I may not have them at this point of time with me because they are not yet implemented. Secondly, it could be the case that even if they are there, then putting their RTL code also with this one is going to make the simulation very slow. So if I can have some abstract behavioral models for those, then during simulation I can take my duty, which is one component of the processor, and plug in the behavioral models of the other components, and then simulate the whole thing, which is going to run much faster. Okay, so that's what is meant by using behavioral models for test bench modules to test structural designs. And you can also use behavioral models for high level specs to drive logic synthesis tools. Okay, so that's something which we will discuss later on. So from the next class we are going to go into behavioral models, and that is where we will start getting more and more flavor of communicating concurrent machines. Thank you. Now ISG is unlikely to return by tomorrow. So in that case, I will take that question.